Hello, my name is Jason McDonald. I'm here to describe my entry for the NXP Hover Games Fighting Fires with Flyers. For this contest, I used the NXP Hover Games drone kit, a Garmin LiDAR sensor, and the MLX thermal sensor. This is a variant of the one that came with the kit. It has a narrower field of view of 35 degrees as opposed to, I believe, 90 of the one that came with the kit. For this project, I wanted to do something simple, something achievable. So what I did is I programmed the drone to create a heat map of the area that it was flying over, and from there it could query the heat map to find the hottest spot on the ground that it's observed. From there it can report back the GPS coordinates of where that hot spot is. It can also create a search routine based on like a coarse grid of heat map, and then it can drop down and do a tighter grid to pinpoint hotspots. To do this, I primarily relied on the thermal sensor, which is a single reading 35 degree field of view MLX heat sensor, and a Garmin LiDAR sensor to give me distance above the ground, and also in the future to do obstacle avoidance and terrain following, so you could send it out without it crashing. And that's basically it. It worked well. And the reason I don't have it here is that in the final, well, one of the later tests it crashed, so it's not here anymore. But there's plenty of video of it actually working. So the way this works is the drone flies around. It continually reads from this thermal sensor, and it takes that reading and couples it with the GPS to get a position, the LiDAR to get a distance above the ground, and the vehicle attitude to get a projection of where the sensor is pointing relative to the vehicle. So say the vehicle is going forward and the sensor is pointed backwards a little bit, it can account for the fact that it's pointing backwards a little bit by using the attitude reported by the vehicle. So what I do is I take that 35 degree field of view, I project it down onto the ground onto an imaginary grid, and I determine the size of that spot and the shape of that spot by knowing how far away I am from the ground with the LiDAR and the vehicle attitude. What this does on a companion computer, if I have it, I don't, where is it? Anyways, it's a Raspberry Pi. There's a Raspberry Pi that sits on board and talks to the flight controller via serial, and it does all the computations and creates the heat map in real time. As it makes an observation of the ground, it'll record which points on the ground had a thermal sensor reading, and it will only store the points that it's seen. So in that way, the map stays as minimally sized as possible, and easy to search. The way that the map is constructed is, I would say, akin to Bayesian inference, if you recognize the term. As I was explaining, this is kind of like a Bayesian inference routine. What it'll do is it'll take a reading of the temperature for a spot on the ground, and all the points on the ground within that spot, it'll assign the average temperature. And then as the vehicle moves around and takes more readings, the future observations of the same point will be in a spot that's in a slightly different orientation. It's moved, it's shifted. And so if that spot appears in observations more frequently with higher temperatures than the surrounding area, then it is more likely that that point on the ground is contributing to the higher average temperature within the reading. So what I do is I take all the readings, all the temperature averages that spot has seen, and I add them all together and divide by the number of times that spot has been observed. And what that tends to do is the spots that are contributing to heat will remain warm on the heat map, and the spots that are cool or contributing to the cold remain cool in the average. And so that way you get a heat map that kind of updates as it flies kind of the probability that any particular spot is warm or cold. And it doesn't take much. You can see one of the videos. I think I've linked a vlog list, but at the very end of the final vlog where it crashed, you can see a video of how this heat map is coarse in the beginning, and then as it moves back and forth doing a survey and it sees the same spots multiple times, the resolution on the heat map goes up dramatically, to the point where I was able to pull out the GPS coordinates for the charcoal fire that it was flying around from 20 meters up or so, and go there, and it was within about a meter of where this small charcoal fire was. And the charcoal fire was only, about that big around. And yeah, that's pretty much it. I think there was some cleverness involved in the coding, I think, but it worked out well. Just using an inexpensive MLX heat sensor with 35-degree field of view and flying around, it was able to create the heat map and pull out the GPS coordinate. And I think moving forward, the only real requirement to get this to work consistently is cheap off-the-shelf hardware like a Raspberry Pi. I was using the Raspberry Pi 3 model A+, which I believe is $20, something like that. But I had done some original testing with the Raspberry Pi Zero W, which is only a $5 board. I haven't had a chance to run the full code on that, so I know Mavlink and all that stuff works on it, but I don't know if you can generate the heat map in real time. There could be some memory issues, but I did my best in the coding to make sure that memory wasn't too big of an issue. Yeah, so I hope you appreciate the project, and it was really fun. It was a big learning experience. Before August, before this thing started, I had never touched a drone, and so I went from zero to autonomously creating a heat map in a few months. So I'm pretty proud of myself. All right, thank you for your consideration, and that is it. Bye.